All right, here we are again. It is June 21st, 2016, and we are here again for another episode of Engineering Statics. So, let's see. Today we are going to begin by going over some problems over the method of joints and some basic truss theory. Then we're going to move on to exploring some more truss theory and a description of the method of sections. Then we're going to finish up by covering working through some problems on the method of sections. All right, so let's begin here. All right, observe this truss here. Determine the force in each member of the Pratt roof truss shown. Determine whether each member is in tension or compression. So, let us observe. So I'm going to first say that I'm looking at this and, oh my gosh, something pops out at me. What pops out at me about this truss? It's symmetric. Yes, exactly. It is a symmetric truss. So therefore, we will be able to use arguments based on symmetry. So I can immediately determine their reactions without doing a balance of moments or anything like that. So I'm simply going to add up all of these to 5.7 plus 10.5 plus 9.6 plus 10.5 plus 5.7. Add those all up. Let's see, just 42. 10, just want to double check. Just 2 plus 9.6 is indeed 42. So that all of these vertical loads sum up to a total of 42 kilonewtons. Therefore, each reaction here, each vertical reaction, must be 21 kilonewtons. Must be 21 kilonewtons. Like so. Now we could draw a global exploded view of all of the forces of all of the joints and all the trusses, all of the joints and all of the members in the truss. But for brevity's sake, I am going to simply draw free body diagrams joint by joint, working our way across the truss. So I'm going to work left to right, and then when I get the force for this one, I'll know the force for this one. When I get the force for this one, I'll know the force for this one, etc., etc., etc. Why am I working left to right? Either doesn't matter. Either one will work just fine. I could work right to left. I could work left to right. It doesn't matter.
The fact that H is on a roller rather than a pin doesn't make any difference?
The question was the fact that H is on a roller rather than a pin will make a difference. In this case, no. If there were horizontal loads on here, then it might actually matter. But here, there are no horizontal loads. So therefore, there are no horizontal reactions to consider. So this support has the same loads as this support, so it's symmetric. It doesn't really matter which end we start on, even in terms of, well, even in a non-symmetric truss, whatever end you start on will still allow you to get adequate loads. Will still allow you to get how shall I say, will still allow you to get the correct results. But some methods are more concise than others. Okay, or actually, I wonder. Well, actually, you know what? I think we might be able to do a little bit better. Now that I'm looking at this, I think we might be able to do a little bit better than that. I'm thinking a little creatively.
One question.
Yes.
DE is shown as a zero force. Can you tell that by inspection?
By inspection, yes, you can tell that member DE is a zero force member. See, looking upon this, what I see is that there is a on member DE. Look at this joint here. I have two collinear members. CE and EG are along a straight line, and there is simply just looking at this joint here, there is a third member going into that joint without anything to resist it. So if there were any force in member DE, there would inevitably be some vertical load on this joint, and because these are purely horizontal, there would be nothing to resist that load, so the joint would be moving. So therefore, this has to be a zero force member. Again, up on this joint here, this thing's really complicated, but that doesn't matter. All that matters is if at one end a a member is zero force, then at both ends it must be zero force. Either end can make a member a zero force member, yes.
So is FG 0 as well and BC 0?
FG, is that one zero? Actually, no. The reason for that is because look at this here, that we have a load coming in here. So in fact, though, what we can tell, though, is I can tell that the load right now, you know what, I'm going to do that. I'm going to just put some points on the board, and I'm going to say, well, first I say FDE must be 0, and FG must be equal to, must be equal to FBC, which must be equal to, let's say, that's going to be 10.5 kips compression. Oh, sorry, yes, kilonewtons, yes, yes, yes. 10.5 kilonewtons compression. The member is directly along the line of action of the load. And there are no other, so we have these two collinear members here. So therefore, all of this load is going to go directly into here. This is basically a zero force member system with a load added. So read about that in your book, but that is that's how it's going to work out. So questions on that?
How do we know they're collinear? Because it doesn't state it.
Well, do you know what collinear means?
Yeah, it means that they're in line, but I'm just wondering because it doesn't state that they're collinear. It doesn't necessarily show that they're equal in line. So I'm just wondering, like, could there be a possibility of there being like a slight angle in them?
The question was, how do we know by inspection that they're collinear? Well, one key thing here is that they gave us only a combined dimension. So notice that they didn't give us, this is clearly along the same triangle. It's not that they gave us like one vertical dimension up to this point, and one vertical dimension up to this point. There is no possibility that these are not at the same angle because they have one dimension line. Okay? All right, so we have this. Let me just I'll just cross them out in black as we go. So I don't have room here to write the forces out, so I'm just going to sort of cross them out as we go. We got that one, and we got that one. Okay, I'm feeling adventurous, which is always a dangerous thing. So I think, you know what, instead of starting from, I've changed my mind. Instead of starting from the right end or from the left end, I'm going to start from the center. What do you think? Should I start from the center? Would definitely allow us to get a lot of load. Anyway, or a lot of loads. Let's see. So we have that. Yeah, why not? I'll have fun. According to certain definitions of fun. So let me draw joint D. And the force is going into there. Again, I'm going to start by drawing everything in tension. So at first glance, this seems like a terrible choice of a joint. Why? Yeah, it looks like I have 5 inputs into this thing. But in reality, this isn't that bad. Or actually, wait a minute. You know what? I'm an idiot. This is a terrible choice. I'm sorry. At first, I was thinking we could just balance things out by saying they're equal to each other, but you know what? They're actually that's the other problem. They're equal to each other. So if we do a sum of forces in the horizontal direction, we're just going to get 0. That's a terrible choice. We can't solve that. I lied. Never mind. Okay, so yeah, never mind. Fine, I'll quit being so adventurous. We'll go back to joint A. Let me draw joint A here. A nice, simple, happy joint. We draw trees, happy trees. So I'm going to have FAC, and I'm going to have FAB. Now, let's see. Let's figure out this. Let me figure out this force triangle here of this one. So we're going to have that force triangle for A to B. Let's see. This is 3.8 to 2.4. 2.4, 3.8. That might be something. Let me see. 3.8 over 2.4. I don't know if that's anything good. Oh well, let's just do a 2.4 squared plus 3.8 squared. Okay, so yeah, I guess this isn't a, unless someone else can find one, doesn't seem like a nice.
Wouldn't it be 3.8 plus 3.2? Because that's the.
Oh, thank you. Ah, that would change things, wouldn't it? That would actually be a, let's see, 3.2, that'd be a 7, right? 7.
Hmm?
We have to be 1.2.
Uh, well, let's see. It's not halfway up, though. So the forest triangle here, let me just erase this thing again. Again, we're concerned about the line. We're not concerned about the actual dimensions about member AB. So the forest triangle here is going to have dimensions, or ratios, 7.0. That comes from 3.2 plus 3.8 and 2.4.
Yeah.
Huh?
Well, I thought we were just going from A to B.
Again, we're not concerned about the actual member. We're concerned about the angle of the member, the line of the member. Plus 7 squared. And this is exactly 7.4. Let's see here. 7.2, 7.4. Okay, 7 over 2.4. Nah. Okay. All right. So we have the forest triangle. 7.0, 2.4, and 7.4. All right, and so now I'm just going to, oh, and then the other loads, of course. We're going to have a vertical load of downward 5.7 kilonewtons and an upward load of 21 kilonewtons. Now, I probably should have drawn that arrow first and this force triangle out there, but we're kind of short on space. All right, so I'm going to start by doing a sum of forces in the vertical direction. The reason I'm doing a sum of forces in the vertical direction as opposed to the horizontal direction is that if I do a sum of forces in the horizontal direction, I will have two unknowns and I won't be able to solve it. So I'm going to have negative 5.7 kilonewtons. Negative 5.7 kilonewtons. And let me use the same nomenclature I did yesterday, or the same notation. So I'm going to say the sum of forces on joint A in the y direction is negative 5.7 kilonewtons plus 21 kilonewtons plus, oh, let's say FAB times, that looks like 2.4 over 7.4 over 7.4, like so. And all of this is equal to 0. So then, negative 5.7 plus 21 is 15.3. So FAB, let's see here, will equal negative 15.3 kilonewtons times 7.4 over 2.4 times negative 1 times 7.4 over 2.4. And this comes to negative 47.175 kilonewtons, or compression. And this is also equal to FH. So we have we now have the forces in two more members. So now we have this one and this one.
Question.
Yes.
You're going on your force triangle, you're going 7.4, 2.4, and 7.0.
Mm-hmm.
And the 7.4 goes from A to D.
Yes.
But you're calling it A to B.
Exactly. Again, the force triangle is not based upon the member. It is based upon the line of the member. We're talking about the angle of the member, not the actual dimensions of the member. These are ratios that we're concerned with. The thing is, we could actually try to cut it in half, but the problem is this isn't exactly halfway across the member. This is 3.8 and 3.2. Yes, we could do some trigonometry and say, okay, let's find the actual vertical dimension of this, and that wouldn't be that difficult. It's just similar triangles, but why bother? It's not needed. Okay, so next I am going to do a sum of forces on joint A in the x direction, and I am going to have FAC plus FAB times 2.4 over 7.4. Oh, sorry, 7 over 7.4. Yeah, that looks too much like a y. Let me get rid of that. Let's say 7.0 over 7.4 equals 0. And FAC, therefore, will be equal to negative FAB times 7 over 7.4 equals negative 47.175 times 7 over 7.4. And this comes to, I get 44.625 kilonewtons. And that's FAC. This is tension, which equals FGH on the other side. So we're definitely going to need another slide for this one. All right, moving along. Let's see. So
I have a quick question about what you did at the beginning. So you said at the very top, you said FDE equals 0.
yes, because it's a zero force member.
But then whenever you said, okay, never mind.
Okay,
Sorry.
we good?
Yeah.
Okay. You're fine, you're fine. Yes.
So you said FDE is equal to 0,
Mm-hmm.
right? How can we say that with the vertical load coming down like that?
Again, if something, the question is, how can we say that FDE is 0 when there's clearly a load coming into it? Again, if something is a zero force member by either end, then it's completely a zero force member. It has to be 0. I don't care if there's 10 billion tons on this thing. If there is nothing to resist it, the force in this must be 0. What's going to happen is this load is going to be distributed to these members here. This one, this one, this one, and this one are going to carry the weight, not this one here.
Okay.
All right. Let's see here. What's next? So we've made some good progress. Now, let's see. Ooh. If this what I can do is, I see something that I can do. Look here. If this one is, we know that this one is collinear with this load, so this is going to be the same. However, if I know the force in this member, I also know the force in this member, as determined by this joint. So if I know if I know FAB, I know FBD. Simply because this is effectively a two sets of collinear members. If you have two sets of collinear members, or a force and a collinear member, you're going to end up with them being equal. Let me go over here and talk about this a bit. So collinear members. We talked about zero force members, but let's talk about let's talk about collinear member sets. If two sets of collinear members meet at a joint, then each set will have matching loads. Oh, what happened? Oh man, did I just erase all that? Oops. Okay, I still have that. Okay, good. Sorry about that. Hit the wrong thing. Collinear members. Member sets. If two sets of collinear members meet at a joint, then the members in a set will have the same load. Will have the same load.
Even if they're not the same length.
Even if they're not the same length, yes. What matters is lines. So for example, say I have a joint here. If I have a member here, and a member, I have a member here, and a member here, and a member here, and let's pretend I do this like directly to the center of the joint and whatnot. And these are all meant to be perfectly lined up. I'm terrible at drawing. So let's say this is A, B, C, D, E. FAB equals FBC. It's going to be one set. And FBD will be equal to FBE. And that will be another set. Note, this only works if no other forces or members are present. So if you add another force or another member, this isn't going to work. This is a special condition of 4 members coming into a joint.
Doesn't work if there's a third set of collinear?
If there's a third set of collinear members, this will not work. My gosh, I cannot write today. If no other members or forces are present. Or forces are present. See, the entire foundation of this, the entire theoretical foundation of this is, imagine I were to sum forces on an axis perpendicular to member AC. I would see that these would have a vertical component, and these would not have a vertical component. So if I had a x prime and a y prime axis, if I summed about the y prime axis, these would have a component here, but these would not. So these must be equal and these must be 0 in that axis. If I sum about an axis perpendicular to these, then these will have non-zero force, but this must have a zero force, again in an axis perpendicular to member DE. The book goes into this, read about it there, but that's the basic idea. Also, this applies if one of the members is replaced by a load. By a load. So say we have a joint here again, and I have a member coming into it, member going out of it, and maybe another member coming out of it, but then a load going into it. Load P. So let's say B, C, D. Again, FAB will equal FAC, but FAD will be equal to P. So this load takes the place of one of those members in the collinear member sets. Questions on that? And we're going to apply this in the previous problem. That's what we're going to apply here. See, that's exactly what we have in this system. We already said that force Fg is going to be equal to 10.5 kilonewtons, and that's what we have here. See, if I consider joint F, well, I'm going to have 10.5 kilonewtons, and then I'm going to have FFG, which must be going into the joint as well, equals FFG. And then here I'm going to have, this one here is compression, FH, FFH, and then this one must also be compression, FDF. So this one must be equal to this one. These are collinear member sets, except this 10.5 kilonewton force is taking the place of one of the members here. So in other words, FDF equals FBD based on symmetry, which will be equal to this load here that we calculated previously. Will be negative 47.175. I probably should be writing this in black, but oh well. Kilonewtons compression. So we have those, and we're really almost done. So we now have this one and this one. All that remains is this one and this one. Okay, so let's see. I'm going to do this here. Keep. And I'm going to, as I do this, I'm going to ask you for I'm going to ask you for some references on numbers when I go out to the next slide. Oh, I need to actually delete the previous mark here. Okay, so let's look at this. I need the last one to figure out is is joint C. So let us consider joint C. We will have FBC, which let's see, FBC. Let me show the forces on here. Actually, let me draw this down. Let me draw this in a different location. So I'm going to draw joint C. I just want to make sure I have a lot of room to write. So first, I know that I remember that FAC was in tension. What was the magnitude of that load? This one here, FAC? 44.65 kilonewtons. FBC was compression, and it was 10.5 kilonewtons. Then I'm going to have FCE. And then I'm going to have FCD. And we need to solve for this one and this one using this joint. And our force triangle here, let's see, what is this going to be? This is going to be 3.2 on the horizontal. .2, to me, let's see, that looks like a 2.4. 2.4, and then the square root of 2.4 squared plus 3.2 squared is just 4. 4 here. So 3.2, 2.4, and 4. All right, now let's work through this. Yes? Did we make FACB tension? Did we make FACB tension? What? It is drawn as tension. I have it drawn as tension. This is tension. Okay. So the sum of forces, I'm going to do a sum of forces in the horizontal direction. Actually, no, sum of forces in the vertical direction. Sum of forces on joint C in the vertical direction, because again, that will give me only one unknown. Negative 10.5 kilonewtons plus FCD times 2.4 over 4 times 2.4 over 4. And this is equal to 0. So then, let's see, does this make sense? Compression, yeah, that makes sense. Okay. And then, so then FCD is going to be equal to 10.5 times 4 over 2.4. 10.5 times 4 over 2.4. And I get 17.5 kilonewtons tension. And this is equal to, also equal to FDG. So that's another answer here. So that gives us this one, and previously we got this one, 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 and this one, and this one. And all that's left is FCE. Finally, sum of forces on joint C in the x direction is going to give us negative 44.625 plus 17.5 times 3.2 over 4. That is the x component of the force produced by member CD, plus FCE equals 0. And so FCE is then equal to 44, not 14. Yes?
I might be wrong, but why is that 44.625 negative?
Why is it negative? The question is, on joint C, it's pulling to the left. Okay. Minus 17, but good question. Negative 17.5 over 3.2 over 4. Never be afraid to ask a question. Over 4. 44.625 minus 17.5 times 3.2 over 4. And I get 30.625 kilonewtons tension. And this is also equal to FEG. And now we have completely solved this truss.
Okay,
Hmm?
we use the formula that says that m is equal to 2n minus 3.
M is equal to 2n minus 3.
Yes, it takes the number of pins, multiplies it
Oh,
by 2, and
M,
subtracts 3. That's the number of members.
M plus R is less than or equal to 2J is one I'm familiar with.
Just using the book formula.
Okay.
So it's got 7 pins, or 8 pins, times 2 is 16, minus 3 should be 13 solutions, right?
To determine what exactly? To determine
How many solutions are there supposed to be
how many solutions are there supposed to be?
using that formula?
Okay. Which formula specifically are you talking about? What page? Okay. 287. Okay, let's see. Ah, a simple truss, yes. Number of members is 2n minus 3. And that's for a simple truss. A simple truss, there's a certain definition of that, but okay.
Then it says if you take m plus 3, that gives you the number of solutions.
Number of solutions, that wouldn't make sense necessarily. That would be the number of members, probably, right? M plus 3? Wait, number of solutions. I'm not quite sure what you mean by that. There should be only one solution to a truss, essentially. Mm.
In case of a simple truss, we have that m is equal to 2n minus 3, that is 2n is equal to m plus 3, and the number of unknowns that can be determined from the 3/4 bodies is thus m plus 3.
Where did you see that?
288.
Okay.
Right in the middle of the page.
288, let's see. Ah, okay, gotcha.
So the number of unknowns can be determined from the...
I would think of it, I would shy away from using those. I'm more familiar and more confident using the combined equation m plus r is less than or equal to 2j to determine whether a truss is statically determinate. Let's see.
I'm just looking for loops to make sure I got all the solutions.
Well, what do you mean by number of solutions? By number of solutions, you probably mean the force in each member, right? That's it. That's all there is. So the number of solutions is equal to the number of members in that case, if the truss is statically determinate.
If you were to count your solutions here, would you have...
Let's see. Well, yes, because we literally solved for every member. So let's see, where it says m plus 3. I'm not quite see. Okay, let's see. And the number of unknowns which can be determined from the free body diagrams of the pin is m plus 3. Okay. Again, that's just part of the solution, not the whole thing. Okay. Anyway, I do want to go into that. Let's talk about the theory of static determinacy on trusses. Whether it can be solved or not, essentially. Static determinacy in trusses. The guiding formula is m plus r is less than or equal to 2j. M plus r is less than or equal to 2j, where m is your number of members, r is your number of reactions, and j is your number of joints. And j is your number of joints. So essentially what this breaks down to is m plus r. Each of these represents an unknown. Each member has a certain unknown force, and each reaction represents a certain unknown force. Your joints are what give you your equations of equilibrium, and each one of them give you two equations of equilibrium to solve for unknowns. So ultimately, for a truss to be statically determinate, m plus r must be less than or equal to 2j, and ideally equal to 2j for the purposes of stability. Okay, but you can go into the theory and read more into this in 6.4 and 6.3. Okay. All right. Okay, so that's the basic idea. Now, this would be a similar idea. We could go through here and, oh, actually, I like this one. 6. Yes, this is one with all the zero force members. See, in certain trusses, you can actually what you might call a zero force member cascade or something like that, where things just jump from one to the next to the next to the next. See, look here. We're asked to determine the force in each member of the truss shown. State whether it's in tension or compression. Well, looking here at joint H, I can clearly see that member CH is a zero force member, again, because I have two collinear members and a third joining it. There is nothing to resist the load generated by this member, so therefore this one is 0. Now, let's look at joint C. Since there is, with this thing out of the picture, there is now nothing to resist a load in this member. Again, by joint C. So therefore, this is a zero force member.
Say that again?
This is a zero force member. Again, on joint C, if D is now out of the picture, so you can sort of imagine covering this one up with your thumb. Then, if this one's out of the picture, I now have two collinear members with a third going into that joint. So this is a zero force member.
Which is the collinears?
BC and CD. BC and CD. So now at joint G, with this one out of the picture, now I have this collinear member with this I have this one and this one as collinear members along here, with nothing to resist the force by member BG. Therefore, this one is a zero force member. And then at joint B, the same applies, and this is a zero force member. However, that is as far as we can go.
Why do you build something like that with extra material?
Okay, the question is, why in the world would anyone build such a thing? Because here's the thing. Now, one, we may have different loadings that we'll need to consider. What if I needed this load to be here or here? Then it maybe at this particular arrangement, the loading is loading. There's no loading on this joint. But what if I have loading on this joint? Or in reality, I have to have some sort of loading here from the truss's self weight. Or more importantly, I can say, you know what? Just looking at this chord here is probably going to be. Well, actually, let's think about this. Yeah, this chord here is probably going to be in compression, and this one's probably going to be in tension, right? And so without that, that is a long column. That's a, well, let's see. Let me do some quick math. 36 squared root of 36 squared plus 15 squared. This is a 39-foot long column in compression. Now, you can design columns that tall with a load on them, with a large load on them, unbraced, but those are very beefy columns. You rarely see. I mean, when was the last time you saw a column in a building that was 39 feet high, you know, over 3 stories high, without any kind of bracing on it? Have you ever seen any such a thing? I mean, the only thing that I can think of in my day-to-day that I've seen things like that are some of the enormous columns you see on the freeway, you know, on the big flying overhead ramps and things like that. Those big, huge concrete columns that go up, you know, many stories to carry on the flying ramps and stuff on the interchanges. Yeah, some of those do have unbraced lengths that long or much longer, but they're huge, very beefy concrete columns with a very large moment of inertia, which means they're going to be very resistant to buckling just based off of their own moment of inertia and radius of gyration. So, but the kind of slender elements you make trusses out of, that's not going to work. You would need a ridiculously thick member here. You're not going to do that with a truss. You need something to brace that with. So that's what a lot of this stuff is for. It's there to brace the column, but not necessarily directly carry any load. By adding these members here, let's see, I'd have to think about the load. That's usually there's a, well, actually, let me review that really quick. Let me pull that up. Let me show you something. This is kind of cool. Let me show you Euler buckling. Buckling, where's the simple formula? I believe it's L squared, right? So there, let me find the, here we are. This is something you'll see in a mechanics and materials class, but look here. Euler buckling, the force required to buckle a column, pi squared EI KL squared. You don't need to worry about this, you don't need to know what this is, but suffice it to say, I would like you to sort of appreciate what's going on here. E is a property of the material. You'll have different E's depending on what you make it out of, steel, concrete, aluminum, whatever. I is a section property. It depends on how it's shaped, what size it is, etc. It's a geometric property of the section. We'll learn how to calculate that later in the semester. K is support conditions, whether it's pinned, fixed, whatever. but L is what we're really getting at. L is the length. So in other words, the buckling load on a column, F is the load required to buckle a column, required to fail by buckling, is proportional to the length, is inversely proportional to the length squared. So if you double the length of a column, you have cut its capacity by a factor of 4. So look at this.
Almost like the force of gravity, too.
Yeah, it's almost like the force. It's sort of an inverse square law kind of thing. But look at this. By bracing this here, I have reduced the effective length of the column to 1/3 of its previous length. What that means is simply by adding these bracing members, even if I don't need them to carry any load whatsoever, I have now increased the compressive capacity of this column here by a factor of 9. Simply by adding these members, this column here, now it may not look like a column because it's kind of on its side, but in terms of structural engineering, anything that's taking compressive load is called a column. And so this thing can now take 9 times the load that it would otherwise be able to take. So yes, those can be absolutely essential, even if they're not needed to carry any load themselves, merely for bracing purposes. But anyway, that's beyond the scope of this course. But so yes, it was a simple question, and I just had to go. I'm like, ooh, shiny, go off running. Anyway. But yeah, there's a lot of reasons why you'd want to add members. Sometimes it's just to make sure something is statically determinate. Sometimes it's for bracing purposes, and often it's simply because it's very rare that we'll design a structure for one single load condition. So if this were, say, this kind of looks like a crane or something like that, right? Doesn't this kind of look like a crane? So if you're going to have a crane, well, maybe you'll have the load, maybe the load can be anywhere along here. Maybe it's on a rail or something, like a crane on a dockyard or something. Or if you have a roof, you know, the amount of wind or rain load on there can vary. And so you might be able to draw the loads under one load condition that would have 0 forces in these members. But if I move this load here, what would happen? If I move this load over here, well then these two would be 0 force members. And well, okay, think about that. That's actually kind of funny. If I move this load here, there would be a 0 force in these members, but I wouldn't call them 0 force members. They would be 0 simply because they just happen to not be carrying any load, rather than by geometry, because they're just at this joint there would be no loads going into it, so there would be no loads here. But anyway, if I put this, imagine if I just add a 15 kip load here. Well, now these would each be carrying load. All of these would now be carrying load, and this problem would get a whole lot more complicated. So let's quickly cascade through this. So yeah, we've already seen that this dramatically changes things. Ooh, I like this. This is really cool. You know why? I see a bunch of 3, 4, 5 triangles. Actually, wait. Oh, never mind. I thought I got all excited for nothing. I thought it was 3, 4, 5, but then I was like, oh wait, never mind. This is 15. Fine. At least this one's no. This is not a 3, 4, 5 either. Whatever. Fine. Getting all excited for nothing. Okay. So I'm going to draw a free body diagram of joint D. Yay, trusses. Do y'all know one downside of trusses? A downside of trusses. Time for another tangent. There is one big downside for trusses, especially in building design. One advantage of them is that they are incredibly weight efficient. They're very, very efficient as far as material goes. But there is one very big downside of trusses. Earthquakes, not necessarily. They'll do fine in earthquakes just as well as anything else. Not necessarily a lot of space. Well, sometimes they can take space, but sometimes so can beams and stuff. One of the biggest ones is actually fire. Fire.
Oh, it's all spaced out, so it's really easy to burn it up.
Yes, exactly. See, what happens is, in terms of fire resistance, did you know for example, would you believe me if I told you that a exposed steel truss carrying the same load would actually be more vulnerable to fire than a wooden beam carrying the same load.
Is it the compression of the truss?
It is true. Okay, we're going back to that little theory. This is a little aside. Trusses and fire. This is definitely beyond the scope of this course, but it's kind of cool. What do you want from a civil engineer? Okay, trusses and fire. So, a truss is very efficient, but it's made of slender members, right? It's very common to see floor trusses and things like that. What this means is, fundamentally, because they're made of very slender elements, this means they have a very large surface area to volume ratio. Surface area over volume is big. Just greater than something. It's a big surface area to volume ratio. If you have something like, so this is what a truss would look like. A big wooden beam, however, now it would need to be a pretty hefty wooden beam to carry the same load. And so you'd end up with a big old cross section, to carry the same load as a steel truss. However, you know what? Fire, if there's a fire below this thing, yes, this is going to end up pretty scorched. But it takes a very long time for, if you have a, like a 2-foot by 3-foot wooden beam or something like that, a foot thick wooden beam, it's going to take a long time, especially for its, treated material. It's going to take a long time in a fire before that thing actually burns all the way through. I mean, it's going to, even if you burn through an inch of it, it's still got 98% of its capacity or something like that. This thing burns, yes, it burns, but it burns incredibly slowly. It takes a long, if you've ever, come on, you've all experienced campfires and stuff like that before, and fires and fireplaces and stuff. It takes a long time for fires to burn through big hunks of wood, doesn't it? And so big, heavy wooden beams actually burn quite slowly. It takes a long time for the fire to reach all the way through them. But here's the thing with trusses. They have a very high surface area to volume ratio. This is a very low surface area to volume ratio. It takes a long time for fire can only interact at the surface of the object. It can't burn inside. So it'll take a very long time to burn through. Now, but you might say, some of you were, incredulous, saying, well, steel can't burn. Obviously it can't. Well, at high enough temperatures, iron oxide, but let's not worry about that. At normal temperatures, no, steel won't burn. But here's the problem. If you look at say the temperature of steel versus say, I don't know, the yield stress, it's going to exhibit this type of behavior. Something like that. So now there were a lot of idiots around the time, basically from the year 2001 up to the present, saying, "Oh my God, the World Trade Center was an inside job. Jet fuel can't melt steel beams," and because they just are foolish and they look up the temperature jet fuel burns at, and then they look up the melting temperature of steel, and they say, "Oh, well, obviously this can't have happened because one is bigger than the other." That's true, but they don't know anything about material properties. Yes, it is true that in a normal fire you're not going to melt steel using even jet fuel unless you would need some sort of sealed container like a furnace for that. But you don't need to melt steel to cause a steel beam to fail because the yield stress, the stiffness of the material declines greatly as it heats up. Before, okay, you can think about this. Like imagine I don't know if you've ever been to a Renaissance festival or even if you've just seen like an old-timey movie or something like that, where you see a movie where you see some old-timey blacksmith, right? What do? They take a hunk of iron and they heat it up. They don't really heat it up so that unless they're actually casting something, they don't heat it up to the point of being molten. They just heat it up to the point of being red hot. And suddenly they can form it simply by hammering it, or by working it in other ways. They don't heat it up to the point of being molten, because then they couldn't work at all. It'd be a pile of molten iron on the floor. So they heat it up to the point of it being soft. Well, soft metal can't carry any load. So if you heat metal, if you heat steel up to the point of it being red hot, it is not going to carry any load. It is going to collapse. So this is why trusses, especially steel trusses, are vulnerable to fire. And yes, this definitely goes beyond the scope of this course, but it is kind of, I do like to illustrate why trusses, one of the downside of trusses. In fact, let me do this really quick. And this is, I'm going to go to Google image search. This is a dangerous thing to do during a class. Let's just search for truss fire protectant, fire coating. Let's see. Yeah, look at that. This is good. Look what we have here. This is an example of a fire-protected truss. See, what they've done is they've come here and they built a truss, and after you've laid out the system and installed everything, someone comes along with a big, it's sort of like a sticky concrete mixed with foam, basically, and they spray it with a hose and just cover the truss in a very light sort of foamy concrete. And what that does is that increases the surface area of the truss and coating it with something non-combustible, but you've dramatically increased the surface area of those members without adding much weight. And so by adding a lot more surface area, it makes them much, much, much more fire resistant. And back to the World Trade Center example, the problem from a structural point of view, the problem with that, what happened then was when you had a plane impact, all of this insulation was blown off during the impact, and suddenly you had just raw members exposed to fire, and the rest is history. But anyway, and I'm talking this purely from a structural point of view, not from the human element of the day, obviously, but this is an engineering class, so there you have it. But anyway, so that is one of the downsides of trusses. But that's one of my asides I like to talk about when I talk about trusses.
Class be like this too.
Huh?
You want more classes like this? Huh?
Well, I kind of like the.
She gonna take you out of the electric and put you in civil. That's what she's doing.
It's interesting. Interesting.
Yes, everyone come to civil. It's dang it, what is it doing here? Okay. Everyone come to civil. The water is great in here. Anyway, no, sorry. What that comes from? Somebody was like, "Man, this is interesting. She's trying to recruit us into civil." Okay. Anyway, okay. Back to this example. Let's solve this here. So I'm going to have FCD here, and FDH, and then 15 kips, and 15 kips. Here. Let's see. And the force triangle here is going to be, oh, well, this is going to be a 36 by 15. Yes.
You start at E instead, or sorry, do you start at D instead of E because the number attached is 0? Because AF is not 0. Is that why you didn't start at E?
Oh, why didn't I start at E? Pure preference, doesn't matter.
Okay.
I could actually solve for the reactions force, but first, but meh. Okay. Okay. So you know what? I think I'm going to have a little fun. I think I'm going to solve this one without solving for the reactions at all. Huh. I could solve for the reactions, but sorcery, you say? Okay. Okay. I think I can do that. Let me just double check that. Let's try that. I'm going to try to solve this without solving for the reactions, not for any great purpose other than to amuse myself. So I'm going to do a sum of forces on joint D in the y direction. This is going to be 15 kips, negative 15 kips, and then minus FDH times 15 over 39 equals 0. And that will lead to that FDH equals Okay, well this becomes positive and then negative. So negative 15, oh wow, 15 times 15 over 39, or actually 39 over 15. So just negative 39 kips compression. So this one is 39, negative 39. Because when I bring this over here, it actually when I bring this over here, yeah, okay. And based on the previous theory we discussed, this one is also going to be 39 compression. This one's going to be 39 compression. So we have this one, this one, this one, and these ones will be fairly easy to get. Sum of forces on joint D in the x direction is going to be negative FCD minus FDH, looks like a P, but it's a D, times 36 over 39 equals 0. And so then, let's see, yes,
When you say that they're all equal to 39, you know they're also all in compression.
yes.
Okay.
The question was, I said these were equal. Does that mean they're also in compression? Yes. And again, I'm only able to do that because these are zero force members. FCD then, let's see, is going to be equal to negative FDH times 36 over 39 equals negative 39 kips times 36 over 39, which comes to positive 36 kips, which will be in tension. So this is 36 tension, this is 36 tension, and this is 36 tension. Just right down the line. Pretty nifty, you might say. Next, I will draw joint A. So we now have the truss mostly solved. And I'm going to say, okay, we have FAE, FAF, and FAB.
How did you choose A?
Oh, how did I choose A? Just looked right. No, I just liked that because I saw that there would be only 2 unknowns going into that one. I could choose F, but then I have 3 unknowns. I have the unknown reaction, and I have the unknown force here and here. So there'd be 3 unknowns there. So I'm not going to touch that one if I can avoid it. Now I could easily just solve for the reactions. It wouldn't be that hard. In fact, let's see. That's just going to be something. Oh well, whatever. It's fine. We could solve for that pretty easily. Oh, I need my force triangle here. So this is going to be 15, 12, and 15 squared plus 12 squared, 19.2. Blech. 19.21. All right, and then I can simply say, the sum of forces on joint A in the x direction is going to be equal to, that's going to be FAB minus FAE times 12 over 19.21 equals 0. So FAB equals, let's say, that's going to be 36 kips. Oh, wait, FAE. Wait, did I flubbed that one up, sorry. Derp. I'm going for FAE, not FAB. So FAE actually equals FAB times 19.21 over 12. And that makes me happy. So that's going to be 36 times 19.21 over 12, or just 19.21 times 3, and I get 57.63 kips in tension.
How do you,
Hmm?
so FCD is equal to FAB?
FCD is equal to FAB. Yep, just based on the zero force conditions that we've gone along. Okay, so this is, I'm going to try the right side lanted here, 57.63 in tension. And now sum of forces on joint A in the y direction is going to be negative FAE times 15 over 19.21 minus FAF equals 0. And so FAF, that goes to FAF, equals, let's say, negative 57.63 times 15 over 19.21, 15 over 19.21, which is negative 45 kips, which is compression. So this one is 45 compression. And finally, I'm just going to try to squeeze in this joint here. I'm going to try to squeeze this in up here, just keep from having to do this on a separate slide. E here. Again, it only asked us for the forces, not the reactions. So I'm just going to be a wizard and not worry about it. Not worry about the reactions. So this is 57.63, and we have the force triangle here. And then I'm going to have FEF. Yes.
So, oh wait, hold on. Never mind, you're good.
Okay. And then I'm going to have a F, or EY actually. Now, I could put an EX, however, I know that's 0 because if we consider the entire truss as a global free body diagram, like a big solid object, there are no horizontal forces applied. There can be internal horizontal forces, but there is no external horizontal forces because there are no external horizontal loads. So we can have internal horizontal forces, but because there are no external ones, there must not be any horizontal reactions. So I'm just going to do this thing here. I'm going to work on this here. I'm going to work on a free body diagram based on this, or sorry, work on an equation of equilibrium based on this. Sum of forces in the x direction on joint E, I'm going to have 57.63 times, again, this 36 over 39. Actually, no, 12 over 19.21. Plus FEF equals 0. And from this, I can get that FEF, right, actually, let's erase this. FEF equals negative 57.63 times 12 over 19.21 equals negative 36 kips compression. And this is 36 kips compression. Just like so. Or alternately, we could solve for the reactions and work through it in the other direction, but either one is perfectly fine. Questions on that?
Some of the forces in the y direction total then, is it just going to be equal to the load? Or,
The sum of forces in the y direction, essentially I could get that, but all that's going to do is tell me that the reaction here is equal to the vertical component of that force there. Actually equal and opposite, but all right. Other questions? Fun, huh? Okay. Simple trusses. This is a bit difficult to explain, so I'm just going to throw the solution on the website. That's about as good as a explanation as I can give. And then here, zero force members. I'm going to have fun with this one. I'll work through this one really quick. Okay. So we've already talked a bit about zero force members. Let's look at this one. Okay, it's symmetric, so that will help. Joint D. This one here has to be a zero force member because of joint D. Two collinear members here, so that one's zero force. This one, EI has to be a zero force member because of joint E, so that one's out of the picture. With this here, with this joint here, I, with this one and this one out, this one's now a zero force member. So this is just a slaughtering of members here. Joint F, collinear members here and here, and this member is going into there with nothing to resist it, so this has to be a zero force member. Joint G, these are collinear members, and this is going into it with nothing to resist it, so this has to be a zero force member. Now at joint K, with this one and this one out of the picture, we have two collinear members with nothing to resist it, so this one is now a zero force member. Let's see, what else do we have? B to J? Yeah. This one to this one is there's nothing to resist it, so this one is a zero force member. Let's see, what else? Anything else? That might be the limit. Yeah, to me that looks like the limit. Unfortunately, as much as I wish I could eliminate this and this, I think that's the limit. So that would be it as far as zero force members go, unfortunately. But still would make the job a lot easier. Then, let's see here. Where to start? Okay, gotcha. This joint and this joint, collinear members, boom, and boom. Okay, let's see. There have to be more hiding here somewhere. B to what? B to D? B to what? B to G. I don't know if I agree with that. That might be it. I hate to leave it with so few, though. Because again, we have, here, the problem is we have these two here. We have two things going into there, so we can't just rule those out. Well, that's no fun. But such is life. I think that's it. Unless I'm really missing something. I think that might be it. Yeah, that's pretty much it. That's all we can really say, unfortunately. Okay, questions on that? Can you all, unless any of y'all can see any other zero force members, I think that might be it, unfortunately. Yes? Yeah, we're mainly looking for collinear members with only one other member going into them.
So you put something like this on the exam?
Oftentimes I do that. Yeah, oftentimes it's a very easy exam problem where I just put asking you to, here's a truss, tell me where the zero force members are. I like doing that. Okay, so we've gone over a lot of the theory. Let's take a break, and when we come back, we'll look at the method of sections.